Let's wrap up section 3.3 with cofunction identities. Cofunction identities express a unique relationship between sine and cosine, tangent and cotangent, cosecant and secant. To visualize these relationships, we can use the right triangle over here on the right side. Notice on this right triangle we have angle U. Because the sum of the three angles in a triangle is 180 degrees, we could say that in radians, the sum of the three angles of the triangle is pi radians. So if we have angle U here, then this angle could be calculated as pi over 2 minus U. Using this triangle, we can visualize the ratio represented by sine of pi over 2 minus u. From the perspective of the angle pi over 2 minus u, sine is opposite over hypotenuse, or x over r. But if we change our perspective from the angle u, then x over r is adjacent over hypotenuse. Adjacent over hypotenuse describes the cosine relationship. Therefore, sine of pi over 2 minus u is equal to cosine of u. We say that sine and cosine are cofunctions. Let's look at cosine of pi over 2 minus u. So from the angle pi over 2 minus u, cosine is adjacent over hypotenuse. That is the ratio y over r. But from the perspective of u, that's opposite over hypotenuse, or sine. Therefore, cosine of pi over 2 minus u is equal to sine of u. Sine and cosine, then, are an example of a cofunction pair. We'll see a similar relationship between tangent and cotangent. Let's examine tangent of pi over 2 on our right triangle. Remember, tangent is TOA, or opposite over adjacent. So tangent of pi over 2 minus u gives us the ratio x over r. But from the perspective of angle u, that's adjacent over opposite. So tangent of pi over 2 minus u is equal to cotangent of u. And with similar analysis, we would find that cotangent of pi over 2 minus u is tangent of u. So tangent and cotangent make a cofunction pair. And because the relationship between sine and cosine as cofunctions, you can also imagine cosecant and secant will have a cofunction relationship, and that is true. Cosecant of pi over 2 minus u is equal to secant of u, and secant of pi over 2 minus u is equal to cosecant of u. So cosecant and secant also make a cofunction pair. Of the three pairs of cofunctions, most interesting, in my opinion, is the relationship between tangent and cotangent. Not only are they cofunctions, but they are also reciprocals of each other. Now, we've looked at each of these identities using radians. In the perspective of an angle measured in degrees, we would simply replace pi over 2 and all of the identities with 90 degrees. That'll be helpful to know as we work example 7. In example 7, we're going to match the expressions on the left with an equivalent expression on the right. And please correct my mistake on H, option H over here on the right. This section has had a lot of typos. I'm really sorry about that. So our goal in example 7 is to apply our cofunction identities and match it up with something equivalent on the right. So cosine of 44 degrees can be written as sine of 90 degrees minus 44 degrees. Notice I've switched from cosine to sine, and I'm subtracting the angle from 90 degrees. Sine of 90 minus 44 becomes sine of 46 degrees. And sine of 46 degrees is down here in option G. On example 2, we have sine of negative 46 degrees. Now, before we can apply our cofunction identity, we need to start with our odd identity. Sine of negative 46 degrees, because sine is odd, is negative sine of 46 degrees. Then we can apply our cofunction identity. We're going to change the sine to cosine and subtract the angle from 90 degrees. 90 degrees minus 46 degrees gives us negative cosine of 44 degrees. And as you can see, that's option B. Anytime we have a negative angle, our even and odd identities will come in handy, and that's what we're going to run into with cotangent of 134 degrees. In terms of its cofunction, this is tangent of 90 degrees minus 134 degrees. 90 minus 134 gives us negative 44 degrees. And because tangent is odd, we could rewrite that as negative tangent of 44 degrees. And that's right here, option C. Working next on sine of 136 degrees, its cofunction is cosine, so we'll take 90 degrees minus 136 degrees. And that gives us cosine of negative 46 degrees. But because cosine is even, this is the same as cosine of 46 degrees. So we'll take this corrected option H, and we are on our way. Paying close attention to the next example, notice the 1 in parentheses does not have a degree symbol. Therefore, we understand it to be in radians. So when I rewrite this in terms of its cofunction cosecant, we're going to subtract that angle not from 90, but from pi over 2. Now, if we get a common denominator between pi over 2 and 1, we could write that pi over 2 minus 2 over 2. And then combining our fractions, not cosine here, how about cosecant? Pi over 2 minus the common denominator of 2. So that matches option F. Be sensitive to degrees and radians. Problem 6 is also in radians. Tangent of pi over 7 in terms of its cofunction is cotangent of pi over 2 minus pi over 7. To combine those fractions, we need a common denominator of 14. For the first fraction, if we multiply the denominator by 7, we'd multiply the numerator by 7. To get a denominator of 14 for that second fraction, we're going to have to multiply both the top and the bottom by 2. Then, combining our fractions, 7 pi minus 2 pi is 5 pi over 14. So this one is equivalent to option D. On problem 7, we have cosecant of pi over 2. The cofunction for cosecant is secant. So we're going to change the function, and then we're going to subtract the given angle from pi over 2. Notice that gives us secant of 0. If we go ahead and evaluate secant of 0, we would end up with 1. And notice up here, option A, cosine of 0 is also equal to 1. So problem 7 is equivalent to option A. And for our last one, again, notice we have a negative angle. So before we apply our cofunction identity, we're going to apply our odd identity. Sine is odd, so I can rewrite that as negative sine of 44 degrees. Then we can change it from sine to its cofunction cosine by subtracting the angle from 90 degrees. 90 minus 44 degrees gives us 46 degrees. So negative cosine of 46 matches up perfectly with option E. Along with new identities, we also have the ability to access these identities to verify other identities. So let's practice verifying an identity using our new cofunction identities. We'll continue to use the two-column format. On example 8a, we have cosine of x minus pi over 2 equals cosine of x times tangent of x. Although there are several ways to work this identity, I'm going to attempt to use our new cofunction identities to verify this one. So we have cosine of x minus pi over 2. I'm going to start with this side and show step by step that it can be transformed into the right side. Now, in all of our cofunction identities, the argument starts with pi over 2 minus something, and we have just the reverse of that in this argument. So what we can do is be really clever with our algebra here. I'm going to factor a negative 1 out of those two terms within the argument. So think of dividing x by negative 1. That would give you a negative x. Negative pi over 2 divided by negative 1 would give you plus pi over 2. Okay, so just double check that with the distributive property. Negative 1 times negative x is positive x, and negative 1 times pi over 2 is negative pi over 2. So what we've written is equivalent to the original. Then I can conveniently reverse the order of these two terms and write this as pi over 2 minus x. And it may even be clearer if we write that as negative parentheses pi over 2 minus x. Not a necessary step, but maybe a clarifying step. Then you can see we have cosine of some negative angle. Because cosine is even, cosine of a negative angle is equal to cosine of the positive angle. So this is equal to cosine of pi over 2 minus x. Now we can recognize our cofunction identity. Cosine of pi over 2 minus x is the same thing as sine of x. Now that's all well and good, but remember, our goal is over here on the right side. So thinking about that right side, we have cosine of x times tangent of x, and recall, tangent of x is sine of x over cosine of x. So the cosine of x ultimately cancels over here on the right side, leaving behind only a sine. But we're going to approach that from this direction. That is, we want to rewrite sine of x as cosine of x times sine of x over cosine of x. Now, what we have here is equivalent to the previous step. So we haven't changed anything, we're just rewriting the expression. Don't be tempted to cancel those cosine of x's. I need them because I'm going to show it's equivalent to this one, right? So copy down the cosine of x. Then we can see sine of x over cosine of x is equal to tangent of x. So in our proof, we have shown step by step that the left side can be transformed into the right side. So we have verified the identity. Let's try one more. Example B, we have cosine of x plus pi over 2 equals sine of negative x. In this case, we can use our new cosine of a sum identity to attempt to verify this equation. So once again, I'm going to start with the expression on the left side because it contains more potential for simplification than the expression on the right side. Expanding this with our cosine of a sum identity, we can write this as cosine of the first angle x times cosine of the second angle pi over 2. And then remember, when you have a positive in the argument, it translates into a minus in the expansion. Then we have sine of the first angle x times sine of the second angle pi over 2. We can then evaluate cosine of pi over 2. Recall that cosine of pi over 2 is 0. And we can evaluate sine of pi over 2. Sine of pi over 2 is 1. Now on the left side, cosine of x times 0 is 0, so that whole term is going to disappear. And we end up with simply negative sine of x. Okay, keep your eyes focused on the right side. That's our goal. We know that because sine is odd, we can also write this equivalently as sine of negative x. And we have verified the identity. So in all of section 3.3, make sure you memorize cosine of a sum identity, cosine of a difference identity, and all of our cofunction identities.